Imagine we have a car with a siren, and the siren is blaring, so it produces a sound wave. Sound is longitudinal, and it's also spherical. It travels out in all directions. How do we know? If you wait a little time, this wavefront will travel out in all directions. If the siren keeps on blaring, it will produce a second wavefront a little bit later. We could wait some time, these will spread, and it will produce a third wavefront if the sound keeps blaring. Again, we could wait a little time, let all of these wavefronts spread out, and then a little later, the siren will produce a fourth wavefront. A person standing here on the right will eventually hear these sound waves, and their brain will perceive some siren sound. Now, in that picture, the person and the siren were stationary. What if we have a picture where the car is moving forward? Okay, let's start again. It creates a wavefront, and sound spreads out in all directions. So if we let some time pass, this first wavefront spreads out. But wait a second. While that wavefront spreads, the car travels forward. So the next wavefront is sent out from here. If we let some more time pass, again, sound spreads. Those wavefronts travel. But during the time that they travel, the car moves forward. So the next wavefront is emitted from here. We could let this happen once more. We let some time pass. These wavefronts all travel out. But during that time when they're traveling, the car moves forward, and it emits the next wavefront from here. Consider the person. Do they hear the same pitch? The answer is no. They will receive these wavefronts that I've highlighted in purple. And notice, they are much closer together. They're far more frequent, and they have a much lower wavelength. So this person on the right hears a higher pitch. What if we put a person over here on the left? That person all the way over there will experience different wavefronts. Here in red are the wavefronts that will eventually move out and strike that person on the left side. So what do you notice? These wavefronts are way farther apart. This person on the left will experience a less frequent sound with a higher wavelength. The sound will appear lower in pitch. This is the Doppler effect, and it can be produced with a moving source. Remember, the siren is the source of the waves. Or it can be produced with a moving observer. If the person runs in toward those wavefronts, then she'll intercept them more frequently, and she'll hear a higher pitch. To summarize, the Doppler effect is a change in perceived frequency due to relative motion between the source of a wave and the observer of the wave. There is an equation that allows us to calculate how much higher or lower the observed frequency is. Now, in this equation, f prime, that's the frequency the person actually hears, and f0 is the frequency that's emitted. The unshifted frequency is f0, and f prime is the shifted frequency. C is the speed of sound in the medium, and these are the speeds of the observer and the source. Now, an important principle when we're using this equation is that any approaching velocity is positive and any receding velocity is negative. Let's see what this means. You've got a siren moving toward a person, and the person is running away. Let's say this source of waves is traveling at 25 meters per second. The observer is traveling at 10 meters per second. Where do you plug in the 25 in this equation? Down here for the speed of the source. But do you make it positive or negative? Apply the rule at the bottom. This siren is approaching the person, so we would put in a positive 25 right there. The person is receding away. They're not approaching, they're receding away from the other object, so we would make her velocity negative. And the waves would travel out, and in this case, they would still be higher in frequency. Now let's consider a different example. The siren is moving away, and the person is running toward. The siren is perhaps going at 32 meters per second, the person at 8. This is still the source of the waves. The person is observing the sound. Okay, so when we plug in, what do we use for Vs? The 32, of course. That's how fast the siren, the source, is moving. But do we make it positive or negative? Pause the video and try to figure it out. The siren is receding away from the person, not going toward, so we would plug in here a negative 32. The person has 8 meters per second of velocity, and they are approaching the siren, or trying to anyway, so we would make it positive. And here that is in the equation. Let's visualize the wavefronts, which move way faster than either object. Now, when you look at those, you might say, oh, she definitely sees a longer wavelength. But remember, she's running toward those wavefronts, which tends to shorten the wavelength. But on the whole, with these values, she would still see a lower frequency.